Structure factor of diamond. Consider the crystal structure of diamond. One way to describe the diamond structure is to consider an FCC lattice with a 2-atom basis at 0, 0, 0 and A over 4, A over 4, A over 4, where A is the lattice constant. The basis consists of 8 atoms if the cell is taken as the conventional cube. Part A, find the structure factor S of this basis, the 8-atom basis. Part B, find the zeros of S and show that the allowed reflections of the diamond structure satisfy V1 plus V2 plus V3 equals 4n, where all indices are even and n is any integer, or else all indices are odd. Notice that HKL may be written for V1, V2, V3, and this is often done. And if you look at the data here, you can see if they are all odd, we have a reflection, and when they are all even, when the sum is a factor of 4, we also have a maximum in the diffraction pattern. So we're going to analyze the diamond structure with the point of view of considering an 8-atom basis instead of the 4-atom basis of the FCC lattice, considered as simple cubic, plus the 2-atom basis in the diamond structure. So normally in the diamond structure we have 0, 0, 0, 1 fourth, 1 fourth, 1 fourth. These two atoms form the basis, and we can calculate the structure factor from the underlying FCC lattice structure factor multiplied with that of the basis. And that's what we did in the lecture notes. So here we're going to talk about an alternative view. So first of all, notice that there are 8 atoms at the corners, 1/8 of each inside the cell, so 8 times 1/8 from the corners, 6 atoms at face centers, half of which are inside the cell, so 6 times 1/2 from face centers, and 4 completely inside the cell. Therefore, we have 8 atoms per cell. So this tells us that it can be regarded as a simple cubic lattice with an 8-atom basis. So it's a simple cubic lattice with 8-atom basis. Now we have to find the location of these 8 atoms in the basis. Now we have at 0, 0, 0, 0, 0, 0, the first one. So we add to it 1 fourth, 1 fourth, 1 fourth to reach the second one. And for the underlying FCC lattice, the next one is at basically x equals 0, y equals 1/2, z equals 1/2. And then we add to it 1 fourth, 1 fourth, 1 fourth to reach the fourth one. And then we locate another one at this face center, which is at x equals 1/2, z equals 1/2, y equals 0. We add to it 1 fourth, 1 fourth, 1 fourth to reach the sixth one. And then we have z equals 0, x and y equals 1/2. Add to it 1 fourth, 1 fourth, 1 fourth. We reach the 8th atom in the basis. So these are at 0, 0, 0, a over 4, a over 4, a over 4, 0, 0, 0, a over 2, a over 2, a over 4. So add to it 1 fourth, 1 fourth, 1 fourth. We obtain this one. A over 2, 0, a over 2. Add to it 1 fourth, 1 fourth, 1 fourth. We have a over 2 plus a over 4, 3a over 4, etc. And then a over 2, a over 2, 0, 3a over 4, 3a over 4, and a over 4. So these guys basically belong to the underlying FCC lattice. So we just add the a over 4, a over 4, a over 4 to find the other atoms in the 8-atom basis for this interpretation. So we can note that the underlying face-centered cubic lattice can be regarded as a simple cubic lattice, which is what we did in the lecture notes, with a 4-atom basis at 0, 0, 0, 0, a over 2, a over 2, a over 2, 0, a over 2, and a over 2, a over 2, 0. Now, let's recall the structure factor. The structure factor for this 8-atom basis simple cubic lattice would be sum over J over the number of atoms in the basis 1 to 8, the atomic form factor of the jth atom, e to the minus I reciprocal lattice vector dot product with Rj, the position vector of the jth atom in the basis. The atomic form factor Fj is equal to F because we have all J atoms are identical atoms. So this is for all J because we have identical atoms. Atomic form factor will be the same. So the geometrical structure factor then will become sum J equals 1 to 8, a single F value for all atoms in the basis, e to the minus I G dot Rj, and our reciprocal lattice vector G is of the form HA capital A plus K capital B plus L capital C. The position vectors of these atoms in the basis are 0A plus 0B plus 0C. The second one, R2, is at 1/4 A basis vector plus 1/4 B basis vector plus 1/4 C basis vector. R3, the third one, position vector, is 0A plus 1/2 B plus 1/2 C. The fourth atom position vector is 1/4 A plus 3/4 B plus 3/4 C. The fifth atom position vector is 1/2 A plus 0B plus 1/2 C. The sixth atom position vector is 3/4 A plus 1/4 B plus 3/4 C. The seventh atom position vector is 1/2 A plus 1/2 B plus 0 C. And for the eighth atom position vector, we have 3/4 A plus 3/4 B plus 1/4 C. And if we have the dot product of reciprocal lattice basis vector A with the direct lattice basis vector A, that dot product is 2 pi. And similarly, capital B dot B is 2 pi, capital C dot C is 2 pi, and capital A dot B is 0, etc. So we have this result. Now we can write the geometrical structure factor Sg in F parentheses exponential minus Ig dot Rj So for the first atom, since the position vector is 0a plus 0b plus 0c, we have exponential minus I, 0. The second term, exponential minus I, the second atom is here, 1/4, 1/4, 1/4. So taking the dot product with HA plus KB plus LC, for example, from HA, 1/4 times 1/4 times A vector will give us pi over 2. So we will have e to the minus I pi over 2 for H plus K plus L, considering this dot product. And for the third term, we have exponential minus I. 0a gives no contribution, 1/2 b gives us a contribution of pi, because b dot b is 2 pi, 2 pi divided by 2 will give us a contribution of pi, and the same would be for the c vector, so this will give us k plus l. And the fourth one will give us exponential minus I, because we have 1/4 again, pi over 2. From the dot product of A with A, we will get an H. From B and capital B and B, we will get 3K. And from C, we will get 3L. So this is the fourth atom contribution. Now we can continue with the fifth atom contribution. We will have exponential. The fifth atom is here. So the 2 pi divided by 2 will give us a pi. Exponential minus I pi. And we have only the x term and z term. So this will give us h and l. So this will be h plus l. The sixth term will be exponential. The sixth one is here, so this will give us pi over 2. 2 pi over 4 gives us pi over 2. So this will be exponential minus I pi over 2. And from the 3 over 4a, we will get 3h. So 3h plus from 1 over 4b, we will get a k. And from the other one, 3 over 4c, we will get a 3l in the dot product. And the sixth term is exponential minus I pi h plus k. For the seventh term, you can see here, this will give us a pi. 2 pi over 2 gives us pi. H and k, there will be no L contribution in the dot product. And finally, the last term is exponential minus I pi over 2, 3h plus 3k plus L. How so? Because we have 3a, 3b, so 3h plus 3k plus L, and 1 over 4 will give us 2 pi over 4 pi over 2, so this term. So we can put this all together. For the geometrical structure factor, we have f times 1 plus e to the minus I pi over 2 h plus k plus L plus e to the minus I pi k plus L plus e to the minus I pi over 2 h plus 3k plus 3L plus e to the minus I pi h plus L plus e to the minus I pi over 2 3h plus k plus 3L plus e to the minus I pi h plus k, And finally, we have e to the minus I pi over 2, 3h plus 3k plus L. And this basically is our final answer for the expression for the geometrical structure factor, considering the diamond structure with an 8-atom basis in the form of a simple cubic lattice. Now we can move on to part B. What we would like to do is find the zeros of the geometrical structure factor. So let's try a mixed parity. So for example, H is even, K is odd, L is odd. For example, 0, 1, 1 planes. Okay, so if we consider this scenario, let's see what this gives us for the geometrical structure factor. F times 1 plus, so we will get H, 0, K and L being 1. This will give us 2. 2's will cancel, e to the minus I pi. 1 plus e to the minus I pi. For K and L being 1, we have the next term e to the minus I 2 pi. And for this term, H is 0, K and L are 1. 3 plus 3 gives us 6 divided by 2. That is 3 e to the minus I 3 pi. So if we continue like this, the next term is e to the minus I pi, e to the minus I 2 pi, e to the minus I pi, and e to the minus I 2 pi. Okay. So, for example, if you think about the last term here, H is 0, K is 1, L is 1, so that gives us 3 plus 1, 4 over 2, e to the minus I 2 pi. So what are these terms? In F parentheses, we have 1 plus e to the minus I pi, that's cosine pi, minus I sine pi, that's minus 1. E to the minus I 2 pi, on the other hand, cosine 2 pi minus I sine 2 pi is plus 1. And then e to the minus I 3 pi, cosine 3 pi gives us a minus 1. Cosine pi gives us another minus 1. E to the minus I 2 pi gives us a plus 1. E to the minus I pi gives us a minus 1. And e to the minus I 2 pi gives us a plus 1. So let's see here. This cancels with this. This cancels with this. This cancels with this. This cancels with this. And we're left with a geometrical structure factor of 0. So we can see that H odd, K even, L odd, and H odd, K odd, L even would give the same result. Here is another example. H odd, K even, L even. For example, 1, 0, 0. Okay, so let's think about this scenario. Just to be sure here, the geometrical structure factor will be then F times 1 plus H is 1, K is 0, L is 0, so this gives us e to the minus I pi over 2. e to the minus I pi over 2. The third term, k and l are 0, so this gives us a 1, e to the I0, that's 1. And if we continue, the next term is e to the minus I pi over 2. The next term is e to the minus I pi. Then we have e to the minus I 3 pi over 2. Then we have e to the minus I pi. And then we have e to the minus I 3 pi over 2. So let's check this last one to make sure. The last one is 3h, that is 3. The other ones are 0, e to the minus I 3 pi over 2. So you can see this result here. So what are these numerically? We have 1, e to the minus I pi over 2 cosine pi over 2, that's 0, minus I sine pi over 2, that's minus I. And then we have a plus 1, e to the minus I pi over 2, again minus I. Then we have e to the minus I pi cosine pi minus I sine pi, that is minus 1. E to the minus I 3 pi over 2 cosine 3 pi over 2 0, minus I sine 3 pi over 2 gives us a plus I, and minus 1 plus I again. So if I look at these in pairs, I see that this plus 1 and minus 1 cancel, plus 1 and minus 1 cancel, minus I plus I, minus I plus I. I'm left with 0 again. So similar result would hold for H even, K odd, L even, and H even, K even, L odd. Okay, so we can see that the zeros occur for mixed parity in HKL values. So we were asked to find the locations of the zeros, and that's where the zeros are. Mixed parity in HKL values, that's when we obtain the zeros. So let's take a look at now HKL all odd. For example, we have 1, 1, 1. Now, for this case, the geometrical structure factor, when I substitute 1, 1, 1 for HKL, gives me F times 1 plus, so let's look at the second term here, 1, 1, 1, that gives us e to the minus I 3 pi over 2, e to the minus I 3 pi over 2, and if we consider the rest, we get e to the minus I 2 pi, e to the minus I 7 pi over 2, e to the minus I 2 pi, e to the minus I 7 pi over 2, e to the minus I 2 pi, and then finally we have e to the minus I 7 pi over 2 again. And I note here that e to the minus I 7 pi over 2 is the same thing as e to the minus I 3 pi over 2, because we have a period of 2 pi in sines and cosines. So if you add 2 pi to 3 pi over 2, you will get 7 pi over 2. So what are these numbers numerically? This is f times 1 e to the minus I 3 pi over 2, it gives us a plus I. E to the minus I 2 pi gives us a plus 1. So next one is plus I. Then we have plus 1, plus I, plus 1, plus I. So what this gives us is basically 4f times 1 plus I, which is 4f times 1 minus I sine 3 pi over 2. So this is what we obtain. So this is one possible answer for f1 plus I. On the other hand, if I try another example, 3, 1, 1. For this one, the geometrical structure factor is f times 1 plus e to the minus I 5 pi over 2 plus e to the minus I 2 pi plus e to the minus I 9 pi over 2 plus e to the minus I 4 pi plus e to the minus I 13 pi over 2 plus e to the minus I 4 pi plus e to the minus I 13 pi over 2. So if you want to check this last one here, for example, 3, 1, 1. So 3 times 3, 9 plus 3, 12 plus 1, 13 pi over 2. So that's basically what I see here for the last term. So if I calculate this, this is f times 1 plus cosine 5 pi over 2 minus I sine 5 pi over 2, that is 1 minus I. And if I continue, it's 1 minus I, 1 minus I, and 1 minus I. So what do I obtain here? This is 4f times 1 minus I, or 4f times 1 minus I sine pi over 2. So what is the conclusion? We have two possible answers for f1 plus I, for f1 minus I. The geometrical structure factor is 4f 1 minus I sine n pi over 2, where n is odd. So it can be 1 pi over 2, it can be 3 pi over 2, etc. So this gives us, in other words, the geometrical structure factor of the form 4f 1 plus or minus I. So when these are all odd. And this would correspond to an intensity in the diffraction pattern, because the intensity is proportional to absolute value of Sg squared, that's amplitude squared. It's 16 f squared 1 plus I times 1 minus I, which gives us 32 f squared, and reflections from these planes are allowed. So that's the conclusion. Now let's go to the case when H, K, and L are all even. Okay, so let's try, for example, 2, 2, 2. So this would have a geometrical structure factor f times 1 plus, let's just look at the first term here, 2, 2, 2 becomes 6 divided by 2 e to the minus I 3 pi. And if we continue this calculation, next term is e to the minus I 4 pi, then we have e to the minus I 7 pi, e to the minus I 4 pi, e to the minus I 7 pi, e to the minus I 4 pi, e to the minus I 7 pi. Okay, so if I look at, for example, the last one here, that is going to be 2, 2, 2. So this gives me 6, another 6, that is 12 plus 2, 14 divided by 2, that is 7. So e to the minus I 7 pi is what I would find. And what is the numerical answer for the total geometrical structure factor? It's f times 1 e to the minus I 3 pi cosine 3 pi gives us a minus 1. And then we have plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. They cancel out in pairs, 0. So this doesn't work. Okay? So here is another 0 situation. Now, if I try HKL all even, and H plus K plus L is equal to 4 times N, where N is an integer. For example, the given data was for 2 to 0. So let's try this one. For this one, the geometrical structure factor becomes F times 1. So 2 to 0, so let's try 2 to 0 here. 2 to 4 divided by 2, that gives us e to the minus I 2 pi. E to the minus I 2 pi. If I continue, I find another e to the minus I 2 pi, then I find an e to the minus I 4 pi, e to the minus I 2 pi, e to the minus I 4 pi, e to the minus I 2 pi, e to the minus I 6 pi. That's the last term I find. And this corresponds to F 1 plus 1 plus 1 plus 1 plus 1 plus 1, 1, 2, 3, 4, 5, 6, 7, 8. That is 8F. And the corresponding intensity is proportional to 64 F squared. So this basically tells us that H plus K plus L must be equal to 4 times N. This implies H over 2 plus K over 2 plus L over 2 is equal to 2N, which is even. So that's basically the same condition found in the lecture. So when we have HKL all even, we have two possibilities. H over 2 plus K over 2 plus L over 2 is odd. Then we have no reflections. H over 2 plus K over 2 plus L over 2 is even. Then we have the geometrical structure factor equals 8F, or we can say H plus K plus L must be equal to 4 times N, where N is an integer. So these two conditions are equivalent. So this is our final answer. Okay, so let's summarize what we did here. We interpreted the diamond structure. Instead of having an underlying FCC lattice with two atom bases at 0, 0, 0, 1 fourth, 1 fourth, 1 fourth, we go back to the interpretation of the diamond structure as a simple cubic lattice with an 8 atom bases that are located at 0, 0, 0, 0, 1 half, 0. So basically the face centers here. So we find these three face centers and we add to them 1 fourth, 1 fourth, 1 fourth. So this takes us to the other atoms. So this completes our 8 atom bases. So these are the proper locations. And those are basically found by looking at the underlying FCC lattice basis atoms when viewed as a simple cubic lattice, and adding to each one a over 4, a over 4, a over 4. And the geometrical structure factor is sum over the number of atoms in the basis, atomic form factor, e to the minus I, reciprocal lattice vector dot product with position vector of the basis atoms, atoms in the basis, and I have written all the position vectors and the dot product with the reciprocal lattice vector, considering the dot product of an A vector with its corresponding reciprocal lattice basis vector, capital A, is 2 pi, otherwise the dot product is 0. The same is true for vectors B and C. I obtain the expression for the the structure factor, geometrical structure factor, when it's viewed from this 8 atom basis point of view. So this last term is 3H plus 3K plus L. So let me clarify that here this is 3K plus L. All right. So first we looked at the mixed parity situation, H even, K odd, L odd. That gave us a 0. H odd, K even, L even, that also gave us a 0. So basically all of these combinations, looking at the symmetry of the sum, gives us 0. So the zeros will occur for mixed parity in HKL values. Now when HKL are all odd, for example 1, 1, 1, or if we consider 3, 1, 1, we see that we have either 4F1 plus I or 1 minus I. So the intensity is proportional to SG amplitude squared, so 32F squared, so reflections are allowed. When HKL are all even, for example, when we try 2, 2, 2, we get also a 0. So we see that there is another possibility of getting a 0 when HKL are all even, but their sum is not equal to 4n. So that is this situation here basically. So this is another answer for SG is equal to 0. So this is another 0 case. Now, when they are all even and their sum is equal to 4n, where n is an integer, for example 2, 2, 0, we have demonstrated that we get 8f for the geometrical structure factor. 64f squared is what the intensity is proportional to. So basically we can summarize our result as h plus k plus l is equal to 4n, n is an integer, and hkl all even. If h over 2 plus k over 2 plus l over 2 is odd, then this would not be equal to 2n. Then that would give us a 0 geometrical structure factor. If it's even, then it's the same condition that we have written here. The geometrical structure factor is 8f.